Welcome to this walkthrough of LeetCode problem number 1316, distinct echo substrings. In this problem, we'll explore how to identify and count all unique echo substrings in a given text. We'll discuss the approaches, analyze the complexities, and provide insights into solving this interesting challenge. Let's dive in. In this problem, we are given a string called text, and our goal is to determine the number of distinct echo substrings within it. An echo substring is a substring that can be expressed as the concatenation of a string with itself. For example, the string abcap is considered an echo substring because it can be written as ABC followed by another ABC. Similarly, the string abab is an echo substring because it can be expressed as ab concatenated with ab. What we need to return is the count of all the distinct echo substrings present in the input string. The input consists of a single string made up of lowercase English letters, and its length can range from 1 to 10,000 characters. The output will be an integer that represents the total number of distinct echo substrings. To better understand the problem, let's look at a few examples. In the first example, the input string is abcap. The distinct echo substrings that can be found in this string are abcap, capca, and capcab. For abcap, it is formed as ABC concatenated with another ABC. Similarly, capca comes from two copies of ca, and capcab is formed by repeating cab. Since there are three distinct echo substrings, the output for this example is 3. Now, consider a second example where the input string is abab. Here, the output is 2 because there are two distinct echo substrings, abab and bab. The substring abab is formed by concatenating ab with another ab, while bab is formed by combining two copies of ba. Moving to a simpler case, if the input string is AAA, the output becomes 1. This is because the only echo substring is aa, which is formed by repeating a. It's important to note that even though multiple overlapping occurrences of aa exist in AAA, we only count distinct substrings, so the output remains 1. Let's now go over the constraints and some edge cases to clarify the problem further. The length of the input string is guaranteed to be between 1 and 10,000 characters, and it consists solely of lowercase English letters. For edge cases, consider a string of length 1, such as a. Since an echo substring requires at least two identical parts, the output for such strings will always be 0. For a string of length 2, like AA, there can only be one echo substring if both characters are the same, as in AA forming a plus a. For highly repetitive strings such as AAAAA, the number of distinct echo substrings depends on their unique patterns. On the other hand, if the string has no repeating patterns, such as ABCDEF, the output will be 0 because no echo substrings exist. These constraints and edge cases help set clear boundaries for the problem and guide us in finding an efficient solution. To solve the problem of finding all distinct echo substrings in a given string, we first considered a brute force approach. Here, the idea is straightforward. We generate all possible substrings of the input string and check whether each one qualifies as an echo substring. An echo substring is defined as having an even length, which can be evenly split into two identical halves. The implementation involves iterating through all possible starting and ending indices of substrings, extracting the substring, and verifying if the two halves are equal. We then store each valid echo substring in a set to ensure uniqueness. However, this approach has significant drawbacks, primarily its inefficiency. Extracting all substrings takes n squared time, and comparing halves adds another layer of complexity, leading to an overall time complexity of n cubed, in the worst case. While simple to understand, this method becomes computationally expensive for longer strings or when the input is near its upper size limit, making it impractical for larger test cases. To improve upon the brute force approach, a more optimized strategy involves using a sliding window technique combined with hashing. Here, we only consider substrings of even lengths, as required for echo substrings, and slide a window of these lengths across the string. Instead of directly comparing substring halves character by character, we compute and compare hashes for the two halves of the current window. This can be done efficiently using techniques like rolling hashes or polynomial hashes. If the hashes match, we confirm that the substring is an echo substring and add it to a set for uniqueness. This approach reduces the time complexity to n squared, as the sliding window traversal still involves iterating over the string, but hash computation for each substring is constant time. While this method is faster and scalable for larger inputs compared to brute force, it does require a careful implementation of the hash function and collision handling, which adds some complexity. Another viable solution utilizes advanced string processing techniques, specifically suffix arrays and longest common prefix (LCP) arrays. The suffix array is a data structure that provides an ordered list of all suffixes of a string, which can be used to identify repeated patterns. Once the suffix array is constructed, the LCP array is computed to determine the lengths of the longest prefixes shared by consecutive suffixes. This information helps us efficiently identify potential echo substrings, as repeated substrings with even lengths can be derived from these common prefixes. The time complexity of this approach is O(n) log n for suffix array construction and O(n) for computing the LCP array, making it the most efficient option in terms of theoretical performance. However, the drawback lies in its complexity of implementation. Constructing suffix and LCP arrays requires an in-depth understanding of advanced string algorithms, which can be challenging to implement correctly and debug. After evaluating these approaches, the sliding window with hashing method emerges as the most practical strategy. While the suffix array approach offers superior theoretical efficiency, its complexity makes it less suitable for quick implementation or competitive programming scenarios. The sliding window hashing method strikes an optimal balance between performance and simplicity, achieving O(n)² complexity with relatively straightforward implementation. Key insights that simplify the problem include focusing only on even-length substrings, as they are the only candidates for echo substrings. Hashing further streamlines the process by enabling efficient comparisons of substring halves, and using a set ensures that we automatically track unique substrings without additional overhead. In contrast, the brute force approach, while easy to understand, is far too slow for large inputs. Ultimately, the sliding window hashing approach provides a pragmatic solution that is efficient, easy to implement, and well-suited for both competitive and practical applications. To solve problem number 1316, we need to identify distinct echo substrings in a given string. An echo substring is a substring composed of two identical halves. For instance, in the string abcap, the substring abcap is an echo substring because it can be split into ABC and ABC. Our goal is to find all such distinct echo substrings efficiently. To achieve this, we use a sliding window approach combined with hashing. The algorithm begins with initialization. First, we create a hash set to store unique echo substrings. We also calculate the length of the string and precompute prefix hashes and modular powers. These allow us to calculate substring hashes efficiently later. Once initialized, we proceed to explore substrings of even lengths since only these can form echo substrings. By iterating over all possible lengths and positions within the string, we systematically identify potential candidates for echo substrings. For any substring length L, we define K as half its length, ensuring that the substring can be divided into two equal parts. Using a sliding window, we extract substrings of length L and split them into two halves, left and right. We then compare the hashes of these two halves. If their hashes match, it indicates that the two halves are identical, and the substring qualifies as an echo substring. We add this substring to the hash set to ensure it is counted as distinct. To optimize this process, we rely on precomputed prefix hashes and modular powers to calculate hashes in constant time. This avoids the overhead of recalculating hashes for overlapping substrings repeatedly. By combining the sliding window with efficient hashing, we significantly reduce the computational cost compared to naive methods. The algorithm is designed for efficiency and correctness. First, we focus only on even-length substrings because odd lengths cannot form echo substrings. This eliminates unnecessary computations. Hashing is key to avoiding the inefficiency of direct string comparisons, which would otherwise lead to cubic time complexity. By leveraging precomputed prefix hashes, we reduce substring comparison to constant time. The sliding window technique further enhances efficiency by reusing computations for overlapping substrings, minimizing redundant work. To ensure that only unique substrings are counted, we use a hash set as our data structure. This automatically filters out duplicates. Additionally, we store prefix hashes and modular powers in arrays, which are essential for quick hash updates and ensure the algorithm remains efficient and scalable. We also precompute modular powers of the base value to facilitate rolling hash updates. This allows us to calculate the hash of any substring in constant time, even as the sliding window moves. The time complexity of this algorithm is primarily determined by the two nested loops for substring lengths and positions, resulting in O, n squared. Hash comparisons and set insertions, however, occur in constant time. Thus, the overall complexity is O, n squared. Space complexity is also O, n squared, in the worst case, as the hash set may store all substrings if they are unique. The prefix hash and power arrays require linear space, contributing O, n. Together, the algorithm balances time and space efficiency. For edge cases, if the input string is empty, we return 0 because no substrings exist. Similarly, if no echo substrings are present, as in ABCDEF, the result will also be 0. In cases where the string is made up of identical characters, such as AAAA, we need to ensure that substrings like AA and AAA are counted only once each. The hash set handles this automatically, as it only stores distinct substrings. The code implementation of this algorithm begins by initializing the length of the string and the hash set. We also define the base and modulus for hashing. Next, we precompute the prefix hashes and modular powers. For each even-length substring, we calculate the hashes of the two halves and compare them. If they match, the substring is added to the hash set. This ensures that all echo substrings are accounted for while avoiding duplicates. Finally, the function returns the size of the hash set, which represents the total number of distinct echo substrings. This implementation is efficient and directly applies the concepts of hashing, modular arithmetic, and sliding window optimization to solve the problem within the constraints. The combination of these techniques ensures that the solution is both time-efficient and space-efficient while handling edge cases appropriately. This solution solves the problem by iterating through all possible substrings of the input string text and checking if they form distinct echo substrings. Here's a detailed explanation. 1. Initialization. The variable n holds the length of the input text, and seen is a set used to store distinct echo substrings. 2. Outer loop. The outer loop iterates over all possible starting indices I of substrings in text. 3. Inner loop. For each starting index I, the inner loop iterates over all possible ending indices j, building substrings incrementally in the variable temp. 4. Echo check. For each substring in temp. If its length is even, it is split into two halves. The two halves are compared to check if they are identical. If they match, the substring is added to the scene set. 5. Result. At the end, the function returns the size of the scene set, which contains all distinct echo substrings. This approach ensures correctness by explicitly checking every substring and utilizes a set to handle duplicates efficiently. The time complexity is approximately O, n cubed, for the nested loops, which is acceptable for the constraints of the problem. Here, we start with the Java implementation of the distinct echo substrings problem. First, we import the necessary utilities and define our solution class. The main method, distinct echo substrings, takes a string text as input. We initialize n to represent the length of the string and create a hash set called scene to store unique echo substrings. The outer loop iterates over all possible starting points of substrings in text. Inside this loop, we create a string builder object named temp to dynamically build substrings starting from the current index I. Then, the inner loop appends characters to temp one at a time, effectively generating all substrings starting at index I. Once a substring is built, we check two conditions: first, if its length is even, and second, if the first half of the substring is equal to its second half. If both conditions are met, the substring is added to the scene set, ensuring only unique echo substrings are stored. After all iterations are complete, the method returns the size of the scene set, which represents the total number of unique echo substrings in the input string. This implementation leverages the hash set to efficiently handle duplicates, and the nested loops allow us to systematically examine all potential substrings. While the approach is straightforward, it's important to note that the substring comparisons and dynamic building of substrings make this a computationally intensive solution, particularly for longer input strings. This concludes the Java implementation of the solution. To solve this problem, we start by initializing the length of the input string text as n, which is 9 in this example, and we create an empty set called scene to store distinct echo substrings. The goal is to iterate over all possible starting indices I in the string, from 0 to 8. For the first iteration where I is 0, we initialize an empty temporary string temp. As we iterate through each subsequent character in the string, starting from index 0, we append the current character to temp. For example, for j equals 0, temp becomes a, for j equals 1, it becomes a, and so on. Each time temp has an even length, we divide it into two halves and check if the first half is equal to the second half. If they match, we know we have found an echo substring. For instance, when temp becomes appcap j equals 5, the first half ABC matches the second half ABC, so we add appcap to the scene set. The process continues until j equals 8, but no additional matches are found in this iteration. In the next iteration, where I is 1, we reset temp to an empty string and repeat the process by appending characters starting from text 1. This time, we find a new match, capka. When temp becomes capka, the first half ka matches the second half ka, so we add this substring to scene. Similarly, for the next iteration where I is 2, we again reset temp and start appending characters from text 2. Another match is found, capcab. Here, the first half cab matches the second half cab, so we add capcab to the scene set. From iterations 4 through 8, no new matches are identified. By the end of all iterations, we have 3 distinct echo substrings, appcab, capka, and capcab. The final output is the size of the scene set, which is 3. In this second example, the input string is ababab, which has a length of 6. Again, we initialize n as 6 and scene as an empty set. We iterate over all starting indices I from 0 to 5. For the first iteration, where I is 0, we reset temp and start appending characters from the beginning of the string. As we build the substrings, we find 2 matches, abab and ababab. For abab, the first half of matches the second half of, so it's added to scene. Similarly, for ababab, the first half abab matches the second half abab, so it's also added to scene. In the next iterations, starting from I equals 1, we find one additional match, babab. Here, the first half bab matches the second half bab, so we add it to the scene set. For the remaining iterations, no new matches are found. The final distinct echo substrings are abab, ababab, and babab, and the size of the scene set is 3. In this third example, the input string is AAA, with a length of 3. We initialize n as 3 and scene as an empty set. Starting with the first iteration where I is 0, we reset temp and begin appending characters from the start of the string. As we build the substrings, we find one match, AA. When temp becomes AA, the first half a matches the second half a, so we add AA to the scene set. In the subsequent iterations, where I is 1 or 2, no additional matches are found because the substrings do not meet the criteria for being echo substrings. By the end of all iterations, the only distinct echo substring is AA, and the size of the scene set is 1. This approach relies on a systematic process involving 2 nested loops. The outer loop iterates through every starting index I in the string, while the inner loop builds substrings by appending characters one at a time from index I to j. To determine if a substring is an echo substring, we ensure it has an even length, divide it into 2 halves, and compare the 2 halves. If they match, the substring is added to the scene set, which automatically ensures uniqueness because sets do not allow duplicate entries. Finally, the size of the scene set is returned, representing the count of distinct echo substrings in the input string. To analyze the time complexity of our solution, we need to break it down step by step. First, we have the outer loop, which iterates through all starting indices I in the string text. Since there are n characters in the string, this loop runs n times. For each starting index I, there is an inner loop that examines all possible ending indices j, starting from I and going up to n1. This means the inner loop runs n(i) times for each value of I. On average, this results in roughly n/2 iterations per starting index. Summing up the iterations across all values of I, we get a total of n plus n1 plus n2 plus 1, which evaluates to n*n plus 1/2. This simplifies to n squared for the inner loop. Inside the inner loop, we construct a temporary string temp by appending one character at a time, which takes 1 on average per append operation. These steps give us a foundational understanding of the computational cost involved in the solution so far. Next, we analyze the operations performed on the temporary string temp. After constructing temp, we check if its length is even and whether the first half matches the second half. This validation step requires comparing two halves of the string, which takes len temp time. Since the maximum length of temp can be up to n, this check may take n time in the worst case. Additionally, we store the substring temp in the scene set if it meets the echo substring criteria. Adding a string to a set involves calculating its hash, which is proportional to the length of the string. Hence, this operation also takes len temp, resulting in a worst-case cost of n when temp is at its maximum size. Combining these with the outer and inner loops, we find that the overall time complexity is determined by the nested structure of the loops and the operations within them. Specifically, the outer loop runs n times, the inner loop contributes n squared iterations in total, and each iteration involves substring and set operations that may take up to n. Multiplying these factors together gives a total time complexity of n cubed, in the worst case. Now let's consider the space complexity of the solution. The main contributors to space usage are the temporary string temp and the scene set. The variable temp is used to build substrings dynamically within the inner loop. In the worst case, its size can grow to the length of the input string n, so the space required for temp is n. On the other hand, the scene set is used to store distinct echo substrings. The maximum number of distinct substrings in a string of length n is n asterisk, n plus 1/2, which expands to n squared. Since the scene set stores these substrings, its space usage is also n squared. Adding these two contributions together, we find that the overall space complexity of the solution is dominated by the scene set, resulting in a total of n squared. This gives us a clear understanding of the memory requirements for the algorithm. Finally, let's compare the current solution with potential optimizations and evaluate its best, average, and worst-case performance. The given approach is a straightforward, naive method that exhaustively checks all possible substrings to determine if they are echo substrings. This results in a time complexity of n cubed, as we've calculated earlier. However, more efficient techniques like string hashing using the Rabin-Karp algorithm or suffix arrays can significantly reduce redundant substring comparisons. These optimized approaches can bring the time complexity down to n squared, or, in some cases, n squared asterisk log n, which is much faster for large input sizes. Now, in terms of best, average, and worst-case scenarios, the time complexity remains n cubed, regardless of the input. Even in the best case, where the string is short or contains no echo substrings, the algorithm must still examine all possible substrings. On average, the number of operations performed aligns with n cubed. In the worst case, where the string is long and contains many valid echo substrings, the algorithm performs the maximum number of substring comparisons and set operations, confirming that the n cubed time complexity holds in all cases. One common mistake when solving the distinct echo substrings problem is relying on brute force without optimization. Beginners often use nested loops to generate all possible substrings and then validate each one to see if it qualifies as an echo substring. While this approach may seem straightforward, it results in a time complexity of n cubed, which is impractical for larger inputs, such as when the length of the text approaches 10,000. Optimized methods, like hashing or dynamic programming, are essential to handle such cases efficiently. Another frequent issue is incorrectly handling substring lengths. Remember, for a substring to qualify as an echo substring, its length must be even, since it needs to be split into two equal halves. Checking odd-length substrings is unnecessary and wastes computational resources. Finally, neglecting to account for duplicates is another pitfall. Without using a set or hash table to store substrings, the same echo substring may be counted multiple times. This goes against the requirement to find only distinct echo substrings, leading to incorrect results. Another source of inefficiency is directly comparing substrings character by character. For instance, using string equality checks like S1 equals S2 for every candidate pair can be computationally expensive, especially when dealing with longer strings. Instead, techniques such as rolling hashes or prefix arrays can significantly reduce the overhead by allowing substring comparisons in constant time after pre-processing. It's also important to anticipate and handle edge cases. Examples include strings that have no echo substrings, like ABCD, strings composed entirely of repetitive characters, like AAA, or very short strings with a length of less than 2. Overlooking these scenarios can result in runtime errors or incorrect outputs, so it's important to test for a wide range of edge cases during development. When preparing for interviews, there are a few key insights to keep in mind for this problem. First, recognizing the symmetry in echo substrings is crucial. For any substring, you need to verify if the left half matches the right half. Efficient substring comparison using techniques like hashing is often the key to optimizing your solution. Sliding window approaches combined with hashing, such as Rabencarp, or advanced data structures like suffix arrays are among the most optimal solutions. Each method has trade-offs in terms of time and space complexity, so be prepared to discuss these thoroughly during an interview. Communicating your thought process early is equally important. If you notice redundancy, such as duplicate substrings, mention using a set to store only unique results. Interviewers value clear reasoning and a proactive approach. Additionally, always bring up edge cases during discussions. For example, consider empty strings, strings with no valid substrings, or strings with repetitive characters. This shows that you're thinking comprehensively about the problem. This problem shares similarities with others that you might encounter, and understanding those connections can deepen your understanding. For example, LeetCode number 1044, longest duplicate substring, focuses on finding the longest duplicate substring using binary search and hashing. LeetCode number 1062, longest repeating substring, also deals with substring repetition, though it doesn't require the substrings to be consecutive. In LeetCode number 1392, longest happy prefix, the emphasis is on prefix-suffix symmetry, a concept closely related to echo substrings. Finally, LeetCode number 459, repeated substring pattern, simplifies the idea by determining if the entire string can be constructed by repeating a substring. Exploring these problems can help you spot patterns and develop transferable techniques for solving symmetry and substring-related challenges. There are multiple alternative approaches to solving the distinct echo substrings problem, each with its own advantages and trade-offs. One effective method is sliding window with hashing. Here, you use a sliding window of size 2k to compare the hash values of the left and right halves of the substring. By storing distinct hash values in a set, you can ensure duplicates are avoided. This approach is efficient with a time complexity of O(n) squared when hashing is used, but you need to account for potential hash collisions carefully. Another powerful technique involves suffix arrays or suffix trees. These structures allow you to efficiently identify repeating substrings, though they can be more complex to implement. Finally, dynamic programming offers a more intuitive way to solve the problem. For instance, you could use a DP table where DP, I, J, indicates whether the substring text, I, J, is an echo substring. While this approach is easier to understand, it may require O(n) squared space, which can be prohibitive for larger inputs. Choosing the right approach depends on the constraints and the trade-offs you're willing to make in terms of time and space complexity. Great job following along. To wrap up, we summarized the problem, key takeaways, and insights you can apply to similar challenges. Thanks for watching. Remember to like, subscribe, and keep coding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!